Let's go to next topic, the emission of heat radiation. In this case, in 1792, there is a Perry Prevost. He published one theory, and he says that any body whose temperature is greater than absolute zero temperature, 0 Kelvin, that body has a property that it can emit heat radiation as well as it can absorb the heat radiation. And after that, it is seen that if you remember in 11th standard, we have seen one of the best example. Suppose on this table we have kept this is cup with hot tea. So this is hot tea in the cup that was kept here. Suppose this is a hot tea in this cup, and here at this side we have kept one beaker, or just we can say just we have taken a plate in which we have taken ice cubes. So these are the ice cubes, we have kept it here on the same table. We can say that after some time it is seen that the temperature of hot tea comes to be the room temperature. Why so? Because if whatever be the initially the temperature of the tea is very hot, 100 degrees Celsius, after some time this temperature get dissipated to surrounding. It will radiate the heat to the surrounding. At the same time it will absorb some cooling from the surrounding. That's why the temperature of hot tea decreases when we have put it on the table, and that is nothing but the every body emit radiation as well as absorb the radiation that they want to explain here, and that nothing but emission of heat radiation. This example already we have learned in 11th standard. So what they want to explain here in this topic, they have mentioned something. The body, if it is very hot, the temperature of body is more, it will emit more radiations. Temperature is less, it will emit less radiation. So in your book they have taken an example. The body whose temperature is 800 degrees Celsius, they can emit radiation which are close to visible region. The body whose temperature is 800 degrees Celsius, it will emit a heat radiation that comes in a visible region of spectrum. And if the body has a temperature approximately 3000 degrees Celsius, 3000 degrees Celsius, it will emit a heat radiation, and that heat radiation comes in a white region, or we can say the different colors, red or white. So 800 degrees Celsius energy emitted is in visible region, and the body appears to be red. If we hit a body at 800 degrees Celsius, we can see the color of that body as a red because that comes in visible region of spectrum, but temperature required is 800. And if we hit the same body with 300 degrees Celsius, the temperature increases 300 degrees Celsius, so we get a white color of red hot. So if we hit a material, just one of the best example for 3000 degrees Celsius temperature is what? Tungsten filament. When we switch on the bulb, tungsten filament heated to 3000 degrees Celsius, and we get a white color of light get emitted by the bulb, and that is nothing but this part they try to explain. Apart from that, below that they have mentioned amount of heat radiated by the body depends on some factor. That factors they have mentioned here. So let's see what are the factors. The first factor, absolute temperature of the body, depends on how much temperature is more, it will emit more heat radiation. Second, nature of the body. Nature of the body in the sense what? Whether the material is black body or polished surface, that is nothing but this. Third one, it depends on surface area. Surface area is more, it will emit more radiant energy. And last one, time duration for which body emit radiations. How much time it will emit radiation? On this factor it depends. After that, they have mentioned here one parameter that is said to be emissive power or radiant power. So let's start with what is meant by emissive power. So emissive power, or it is said to be, sometime it is said to be radiant energy or radiant power, I think they have used. So radiant power. So radiant power or emissive power. What exactly radiant power or emissive power means? Amount of heat radiation incident per unit area per unit time at certain temperature is said to be emissive power of that body or radiant power of that body, and represented by the letter R. So these are represented by the letter R, and is said to be amount of heat radiations incident on body per unit area per unit time is said to be radiant power of that body or emissive power of the body. Suppose Q is amount of heat radiation incident on a body whose area is A for T amount of time, then that is their ratio. Q divided by A into T gives the radiant power, or we can say it gives the emissive power of the body. So what exactly emissive power? Amount of radiant energy incident per unit area per unit time is always constant, and that is said to be radiant power of that body or emissive power of the body. So it's they have given the unit watt per meter square, joule per meter per second, and dimensions are L0 m1 t minus 2. So these are nothing but what emissive power of the body. After that, here they have mentioned coefficient of emission or emissivity. Coefficient, this is emissive power, amount of heat radiation incident per unit area per unit time. So that is the radiant power, incident power. Now let's go to next. What is that? Emissive power or coefficient of emission. So coefficient of emission, or it is said to be emissivity of an perfectly black body. Emissivity. So emissivity, so here emissivity or coefficient of emission. What is emissivity or coefficient of emission? It is a ratio of radiant power of the ordinary body to the radiant power of perfectly black body is always constant, and that constant is said to be coefficient of emission or emissivity. So this R is nothing but what? Radiant power or emissive power, okay, of any body. So this radiant power of any body, ordinary body, the ratio of radiant power of ordinary body to the radiant power of perfectly black body is always constant, and that is said to be emissivity or coefficient of emission. So that coefficient of emission represented by E. So we can write E equal to radiant power of ordinary body to the radiant power of perfectly black body. Their ratio is always constant, and that ratio is said to be emissivity of the body or emissive power of the body. For perfectly black body, E equal to 1, that we know. E equal to 1 because it will absorb as well as it will emit everything. So E equal to 1 for perfectly black body, and for perfect reflector and transmitter, E equal to 0. They can't reflect, so that E equal to 0. So here this is nothing but what we have learned about this coefficient of emission or emissivity, and this value of coefficient of emission is generally in between 0 is less than, E is less than 1. In between 0 and 1 its value lies. So the for an ordinary bodies, the value of E is in between this for ordinary bodies, and for copper they have given the value of E is 0.3, coefficient of emission or emissivity. So I think it is sufficient now. Now next period we will start Krichoff's law of heat radiation and its theoretical proof. Okay, so watch my video. After that, just try to read the same topic from the book, and still if you have any queries, you can free to ask. Thank you.